Okay, let's play around a little bit with GeoGebra and see if we can learn something here. I'm going to take the equation of a circle. You may or may not have encountered that yet, but let's look at it. And I've chosen here to construct the circle using the center and a radius. So if I click a center point and put in a radius, taking a circle centered at this point, whose radius is 5. Okay, I can put that point wherever I want. And notice that for that circle, there's an equation over here, which looks a little bit complicated. So let's simplify it to start with. Let's just put this at the origin. And now it doesn't look so complicated. In fact, it looks very interesting. Looks like the equation of the circle looks a whole lot like the Pythagorean theorem. So x squared plus y squared equals 25. So if you know anything about the Pythagorean theorem, it's like if I go over and up, this will give us the diagonal distance. If I take a point on the circle, like if I go over 3 and up 4, that gives me that point. And that distance there would be 5, which is the radius. And so if I actually draw that segment in there, if I highlight this, it's labeling that F, and the length of that is 5. And wherever I put this point, notice that that radius stays 5. So that's the definition of a circle. It's all the points in the plane that are a particular distance from the center point. Now let's take the circle and move it somewhere. And all of a sudden, it looks like it's a little bit more complicated. So let's go back and do this more systematically. What if I just go 1 unit to the right? Then instead of saying x squared plus y squared is 25, it says x minus 1 squared plus y squared is 25. If I go over 2, now it says x minus 2 squared plus y squared is 25. So what are we getting at? Well, x is how far I have to go from the origin out to whatever point I'm talking about. Like take this point right here. So if I subtract the 2, which is how far I'm offset, then that gives me the distance from the center point instead of the distance from the origin. So that's where that x minus 2 comes from. What if I go up 1 unit? Now it says x minus 2 squared plus y minus 1 squared. So for this point, it's telling us how far to the right am I from here, and how far up am I from here. So I'm subtracting off the excess, the 2 and the 1, to get just the distance from here out to that point instead of all the way from the origin out to that point. Okay, so that's the trick here. So if I want to move this circle around, it looks like I could specify where it's going to be by following this pattern. So any place I saw an x, I plug in an x minus the offset and a y minus the y offset. That should do it for us. Let's try constructing this circle from scratch. So let's do this. Let's put a slider here for A and another one for B. And let's construct our center point to be AB. So here's AB. And now I want to construct a circle using an equation that'll be centered at that point. As we saw just a minute ago, I'm going to go parenthesis x minus a and square that. And then plus, so parenthesis y minus b and square that equals 25. All right, and look over here. The a and the b are both 1, and this is x minus 1 squared and y minus 1 squared. And if I slide a and b, it moves back and forth and up and down. Sort of cool. Is this a special property of circles that I can do this? What if I take another familiar looking curve? I think you recognize that's a parabola. Let's try the same trick. So here's the curve, and here it shows you the equation y equals x squared. If I go in there, and in place of x, I'm going to put x minus a. Okay, I'm just making that substitution. And in place of y, I'm going to put y minus b. And what do you know? Look at that. It moves right along with the circle. Okay. If you've had some trigonometry, you know about sinusoidal curves. Y equals sine x as one example. So there's a sinusoidal curve. But what if I want to put that curve somewhere else on the plane? All right, let's come to the equation of the curve. And in place of x, I'm going to put an x minus a. In place of y, I'm going to put a y minus b. What do you know? It looks like I can move this thing around along with everything else. What if our goal is to find the equation of a line with a certain slope that passes through this point? That's a problem you encounter in Algebra 1, and it's one that a lot of students have a lot of trouble with. So let's do a really simple line to start with that goes through the origin, something like y equals mx. I haven't defined m yet, so it's going to create me a slider. Let's just put that over here with these other sliders. And if I change this number, all that does is it affects the slope of the line. But what if I want to put this line through that point? In other words, a line that has this slope, but it goes through a certain point on the plane. So let's take this equation and modify it. So here, instead of y equals mx, I'm going to say x minus a. In place of y, I'm going to put y minus b. I just make that substitution. I'm offsetting it in the x and the y directions by this amount. Wow, there we go. It just took that line and it slid it right up there. Notice what happens. I now have the equation of a line through a particular point. If I look at the equation of the line, it looks the same as what you would derive in Algebra 1, because it's the same result really, but we got at it by thinking about it differently. I started with a simple line through the origin, and I just moved it over here by the same trick that we're using to move anything else. Okay, so moving things around on the plane can be a useful way to conceptualize what we're doing. I want to close with one more example, and this one comes from what I'm actually doing in my physics class. When you get to dealing with waves like sound waves and light waves and so forth, you have sinusoidal curves, but they don't just stay fixed. Let's start with a sinusoidal wave here. Just take y equals sine of x. But I don't want just a fixed sine pattern. I want to have a traveling wave. So how do I move it to the right in a way that it varies with time? Well, let's do what we've been doing. Let's make a new slider and just call it t to stand for time. And I want it to go from 0 at the beginning and just put some big number, like maybe 700, all right? And let's look at the properties here. I want to make the slider itself longer, so let's put 700 there as well. Okay, now I'm going to take this point and animate it. Okay, so notice that the time slides along. I can put it back there, and I can start it, stop it, and so forth. So how do I make this wave itself move to the right with time? Well, in a way it sort of looks like all these other problems. We're going to take a pattern and shift it to the right, but the amount that I shift it to the right is not going to be a constant like a or b. It's going to be t. So let's take x minus t. Okay. Now let's animate the time variable, and there you have it. We can make a traveling wave just by having a function that translates to the right by an amount that's proportional to the time. Isn't that cool? So anytime you have a computer showing you pictures that are moving around and animated and whatever, somebody somewhere is working with equations behind the scenes. So I think that's pretty cool.